Howdy, math neighbors. It's me, your guy, here to bring you another AP Calculus video on infinite series. We're down to the last few topics. And for the interval of convergence, which we're studying today, I wouldn't say these problems are difficult so much as they take a lot of time. Consequently, what I think is going to be best is if I record the video in advance and then let you watch it at your leisure. That way you can pause it, replay it, and maybe even ask me questions during class. We'll kind of see how that goes. So you know how I like to do things. I like to leave everything up you need to see, give you a chance to write. Please pause the video, get all this written down, and then I'm going to talk through it. So picking up right there after you finished writing all of this down, what we're interested in with these approximations is to know when they're valid, because we didn't really talk about it, but even those Maclaurin series we memorized are not good for every value of x. And for our purposes in this class, it's not going to matter a whole lot. But for thoroughness sake, it's well worth the time to invest this kind of knowledge. So we're not surprised later on if this ever comes up in the future. The relevant prior knowledge that you should have written down would be the Taylor formula to generate terms. You can write it in expanded form. You can write it as a simple formula or in summation notation. You already know my preferences, but I'll leave that up to you. These are your notes. You should know what a Maclaurin series is. The Lagrange error bound formula is worth knowing. And then we're going to be making use of not all of the series tests, but a large number of them. And you'll see why in a little bit. But first, three definitions. First definition is a power series. So we have the definition of a power series, but I think the examples make a lot more sense. So the way I think about a power series, and this isn't perfectly correct, is I think about how it makes a polynomial. So we look at the first example right here. We've got some constant value times x to some power. So this first one is x to the 0, x to the first, x to the second, x to the third. So we've seen this a little bit. We saw it with the Taylor series. So something I'd like to note here right now is that a Taylor series can be a power series, but it doesn't have to be. Similarly, a power series can be a Taylor series, but it doesn't have to be. Actually, I need to rephrase that. I apologize. I'm not going to edit this out because I don't care. A Taylor series will be a power series, but a power series doesn't have to be a Taylor series. And if C is the center as per usual, we have this form. So this form is when C is 0, this would be for any value of C. Second new term, the radius and interval of convergence. And I think an example is the best way to understand this. So the overall idea here is a radius and interval of convergence tells us when and for how long we can actually use one of these polynomials to approximate values. Okay, pretty simple. I'm looking at a function on the interval 2, 6, and I know that I've got a Taylor approximation. I know it's going to be accurate. If I'm not on the interval 2, 6, probably won't be accurate. Could it be? Sure, it's possible. Doesn't have to be. So if we look at the interval 2, 6, the radius of convergence is 2 and the center is 4. How did I know that? Well, there's a few ways you could think about it. The center ends up being the midpoint of the interval, and the radius extends an equal distance in both directions, left and right, from the center. So if we look from 2 to 6, we could break that into two chunks of 2, from 2 to 4 and 4 to 6. Or you could say 2 plus 6 is 8. 8 divided by 2 is 4. My midpoint is 4. If I go from 4 to 2, the radius is 2. If I go from 4 to 6, the radius is 2. Same value in both directions. Done and done. We're really not super interested in the radius of convergence. We spend most of our time looking at the interval of convergence. And we have a few examples here to do that. So here's the first example. Oops. I'll just put the whole thing up here. As per usual, my suggestion is pause the video, get all this written down. And before I begin talking here, quick note. The ratio test is generally your best bet. always is perhaps too strong a claim, but I always start with the ratio test nonetheless. Anyway, so if we consider this infinite series, so we're summing from 0 to infinity of n factorial times x to the n, we would like to know the radius and interval of convergence. So how do we do that? Well, we do that by determining when this series converges. And we do that by using a convergence test. And really, any could be used if it applies. But what's going to be best typically is the ratio test. So I set up my ratio test. I do the the a sub n plus 1th term, which is n plus 1 factorial, x to the power of n plus 1, in ratio to the nth term, n factorial times x to the n. And I've written it out here longhand. I'm not doing this for all of the examples. And I encourage you, if you're confused by this, to make sure this is a question you asked to get answered. N plus 1 factorial and n factorial can be expanded like so. The n's, n minus 1's, and everything afterward cancel to 1. So we have n plus 1 divided by 1. It doesn't change the result here, but that is a mistake. And then I have x to the power of n plus 1 divided by x to the power of n. The x to the power of n's, they make 1, so I have x in the numerator. So as n approaches infinity, I have infinity times x, which is infinity. So we know from the ratio test that we compare our result to 1. The value is greater than 1, then we converge. Since there is no x in this statement, there is no restriction on x. So we'd say this converges for all values of x. Our center is 0. I know this because x minus 0 to the n makes that. Our radius is infinite in length, and you could write the interval pretty much however you want. I chose to not use the interval notation we typically use. Okay, so here's the second one. I encourage you to pause the video and try it. After you've tried it, here's the work. Pause the video and get this written down. I'm going to talk. So once again, we have an infinite series from 0 to infinity. We're going to use the ratio test. So I need the n plus 1th term to the nth term. So I have 3 times the power, or 3 times x minus 2 to the power of n plus 1 in the numerator, 3 times the quantity x minus 2 to the power of n in the denominator. The 3's make 1. The x minus 2's to the nth power also make 1. So I have x minus 2 to the first power in the numerator, which as n approaches infinity is unaffected. So I have the absolute value of x minus 2. In order for this to converge, right, we're interested in the interval of convergence. The absolute value of x has to be less than 1. If it were greater than 1, it would diverge. If it equals 1, it would be inconclusive. So we solve this inequality, which means I need to take the negative path, which is the opposite of x minus 2, and the positive path, which is the positive of x minus 2. So opposite of x minus 2, I decided to multiply both sides by -1, which means the direction of the inequality changes. So I'd have x minus 2 is greater than -1, add 2 to both sides, x is greater than 1. Here, add 2 to both sides, x is less than 3. So our interval is right now one of 4 things. It could be this. It could also be this. It could be this. Or it could be this. This is the part that a lot of students forget. And then on their first assessment, they get creamed. You need to remember to check the endpoints of the interval of convergence because right now there are 4 possibilities. We don't know which of the 4 is relevant. We have to determine that. So we determine that by using these values of x in the series. So what I literally do is I take 1, I substitute 1 in. So I have 3 times 1 minus 2 to the nth power. 1 minus 2 is -1. So I have 3 times -1 to the nth power, and I have to use a series test on it. Any series test that applies will do. I chose to use the nth term test, and by using the nth term test, I determined that this diverges. So that tells me that it's not this, and it's not this. Because of x equals 1, the series diverges. So the question is, at 3, does the series diverge or does the series converge? So once again, I literally take the value of x, substitute it into the series. I have 3 times quantity of 3 minus 2, which is the sum from 0 to infinity, 3 times 1 to the nth power. Again, I chose the nth term test. The interval is from 1 to 3. And it's open because if you choose 1 or if you choose 3, you get a divergent series. Here comes the next one. Same thing as before. Get this copied down, try it. So pause the video. Here's the correct work. Consider it. Pause the video. Now I'll talk. So I have x to the power of n divided by n. Even if I didn't know I was doing a radius / interval of convergence, if I wanted to know when the series converges, I would choose the ratio test nonetheless, because it's an nth power and division by n, a mixture of operations. So the n plus 1th term is x to the n plus 1 power divided by n plus 1. The nth term is x to the n divided by n, but since I divide by that, I multiply by the reciprocal. X to the power of n's, make 1 together, n plus 1 and n. If I consider that limit approaching infinity, I apply L'Hopital's rule because it's infinity divided by infinity. So I have 1. 1 times x is x. To converge, the absolute value of x needs to be less than 1. So the negative path, negative x is less than 1, which means x is greater than -1 when I solve, or x is less than 1. Once again, there are 4 possibilities. I can converge at -1 and 1. I could converge at either -1 or +1, or I could converge at neither -1 nor +1. I have to sort that out. How do I sort that out? I take my value of x that I got, both of them, the end points as they're referred to, -1 and 1, and I literally substitute them into the series. So I have -1 to the nth power divided by n. I know that that's a convergent alternating series. If you need to write out the series test to be certain, do so. Always use a series test. Don't just say, yeah, converges. No. Write down the series test. You may not have to write out the entire series test work, but write down the series test and the result. The second one, of course, is the harmonic series, so I always know it diverges. So that means the series converges at -1, diverges at 1. I have the interval closed at -1, open at 1. Note the center is again 0, and the radius is 1. What we're going to do next is look at something similar to what we've been doing, but with a little bit different notation, because I want you to get used to having these same question asked a little bit differently. So here we have a series, an infinite series defined as a function f. We're going to determine the interval of convergence for each function. The first function is f of x. Now f of x, of course, is the same thing we just did, but it's still worth going through the work again. Good practice, especially if you're brand new. For the next example, we're going to consider f prime of x. Now here's what I'd like you to do, as per always. Pause this, try it. Check your work. Pause the video while you do so. If you'd like, I'm going to talk about it. So f prime of x is, as we well know, according to the notation, the first derivative of f. Now, there's a couple of ways you could determine that this series has a formula from 1 to infinity of x to the power of n. The first way I did it was to literally take the derivative of x. So even though the power is n, it still works the same way. Think about it if this was x cubed. This was x cubed, I'd have 3x squared. This was x to the 7th, I'd have 7x to the 6th. That hasn't changed. Just because I'm calling it n doesn't mean we change anything about what we're doing. When we take the derivative of x, we multiply by the previous power n, we subtract 1, get n minus 1, and that's why we have n times x to the power of n minus 1. Since I have n in the numerator and denominator, they make 1 together. Alternately, you could consider the terms. These are the terms for f of x. And again, this is when n is greater than or equal to 1. You could literally take the derivative of each term. The derivative of x is 1. The derivative of x squared divided by 2 is 2x divided by 2, or x. The derivative of x cubed divided by 3 is 3x squared divided by 3, or x squared. The derivative of x to the fourth divided by 4 is 4x to the fourth, or x to the fourth. And from that, I can determine a pattern. Again, the 4s, they make 1. I have x to the fourth. So this first term is 1, n equals 1, n equals 2, n equals 3, n equals 4. So x to the power of n minus 1 works. Now, forgive the mistake here. I incorrectly computed this, but the x to the n's make 1. The 1 minus 1 makes 0, so I have 1 in the numerator and x to the negative first power in the denominator. So I have the limit as n approaches infinity of 1 divided by x to the negative first power, which is x. The absolute value of x has to be less than 1. So x is bigger than negative 1 or less than 1 after solving the inequality. The question is, do we include negative 1 and 1 on our interval of convergence? And the answer is no. How do I know that? I checked both endpoints. I looked at the literal series when x is negative 1. So substitute negative 1 in, negative 1 to the n. Substitute 1 in, 1 to the n. Both are divergent. You could call them divergent geometric series. Absolute value of r equals 1. I chose to use the nth term test again. Last one, try it. Pause the video. Last one, work. Check it. Pause the video. Now I'm going to talk about it. So when you do an antiderivative, what you're doing is you're adding 1 to the exponent, dividing by the reciprocal, or multiplying by the reciprocal of the new exponent. Doesn't matter what it is. If it's x to the fourth, it becomes x to the fifth times 1/5. So if I have x to the nth power, if I add 1, that's x to the n plus 1 multiplied by 1 over n plus 1. You could do it by terms. Here are the terms. Now, some of these are quite difficult, and I recommend using the terms. Some of them you can't find an antiderivative. Well, maybe you could, but it's pretty difficult. So I recommend using the terms. Like I said from the beginning, if you're confused about what a sequence or series is doing, write out some terms. So here's f. Here I have literally taken an antiderivative of every single term. This becomes 1/2 x squared. This becomes 1/2 x to the third times 1/3. This becomes 1/3 x to the fourth times 1/4. This becomes 1/4 x to the fifth times 1/5. So what I have literally happening here, if n is greater than 1, this is n plus 1, this is n, and this is n plus 1. So I have 1 divided by n times n plus 1. X is to the n plus 1th power. If I start at 1, I have 2. 2 has 3. 3 has 4. 4 has 5. So that matches what I got just by taking an antiderivative here. I'm ignoring c because adding a constant has no effect on the convergence or divergence of a series. So I've got an infinite sum. Let's say the value is 5. If I have a constant of 4, that just changes the value to 9. It doesn't change the overall convergence or divergence, the overall value of the series. Either way, we have the same kind of thing happen as before, but this time the algebra is a little bit different. I have x to the n divided by x to the n, that's 1. X to the 2th divided by x to the 1th is x to the 1th in the numerator. N times n plus 1, n plus 1 times quantity of n plus 2, using L'Hopital's rule a couple of times also equals 1. So once again, the absolute value of x less than 1, x is greater than -1, x is less than 1. I literally take these values, -1 and 1, substitute them into the formula, and consider this series. Does this series converge or diverge? How do I know? Again, and finally, you have to use a series test. You can't just be like, yep, it converges. Yep, it diverges. Make sure you have a reason why. The first one is an alternating series that converges. The terms alternate signs. They go from negative to positive. The limit as n approaches infinity of this formula is 0, and the n plus 1th term is always less than the nth term. Formula is decreasing. Here, I can't use the alternating series test, but I can use comparison to 1 over n squared. And if I do, I find that this is larger than this, and this is convergent. I know this because it's a p-series. Should have written that in. Sorry about that. So in this case, both endpoints are closed. Thanks for watching this AP Calculus video on infinite series. Again, watch it as many times as you'd like. Get those watches way up there. Increase my visibility on imaginary YouTube. And don't forget to smash like and subscribe. See you next time.